All right, good morning, everyone. Uh, Glad to be a part of the Autoware tutorial series. So, as Simon mentioned, we'll be talking about a tale of two open source ecosystems, AutoDrive, something that we have been developing over the years, and Autoware that I think most of you would be aware of by now, or would be in the tutorial series anyway. So there'll be two of us talking today. My name is Tanmay. I am a PhD candidate at Clemson University's International Center for Automotive Research. Me and my twin brother Chinmay will be doing the talking today. Some of you might know us by the name Tinker Twins. Our PhD research is targeting digital twins, no pun intended, where I am focusing on the real to sim aspect. Whatever is in the real world, how do you model it, estimate, and then bring it in simulation reliably? And Chinmay is working on other side of the coin to ensure whatever works in simulation can be transferred with guarantees back to the real world. So in today's agenda, we'll be first going over the introduction of what AutoDrive ecosystem is and how it enables research and education. We'll be then talking about some exciting competitions realized by AutoDrive. Most of the talking today will be about AutoDrive Autoware integration, where we'll be highlighting some of the key aspects and demos that we have curated. Followed by that, we'll have a step-by-step tutorial on how you can get started with AutoDrive and Autoware today. And then at the end, we have some exciting unveiling to do. I won't, of course, talk about it now to save the fun for the last. So let's first get into what AutoDrive ecosystem is. For those who don't know, we have been developing this digital twinning ecosystem for a few years now. It started as our research internship at Nanyang Technological University, then continued as our senior design project in our undergrad. And after we joined directly to pursue our PhD at CUICAR, this now is something that we have been developing further. So the picture in the center kind of shows the high level overview of what AutoDrive is. You have different vehicles. These can be physical vehicles as depicted in the first and second column, third column of the picture in the top left, or they could be the digital twins of the same that is depicted in the second and fourth column. So we have different scales and operational design domains that AutoDrive can support. So for example, you have small scale vehicles like Nigel, which is the native vehicle of AutoDrive, as well as F110, both of these being open source. In the mid scale, you have vehicles or robots like the Husky, which is a skid steered robot, and Hunter AC, which now can target both on-road and off-road applications. And in full scale, for example, you have the Open CAV, which is a Chrysler Pacifica hybrid autonomous, which is an on-road commercial vehicle, as well as a Polaris Razor, which is an off-road or off-highway recreational vehicle. Next, coming to the infrastructure, you have different ways of modeling it and simulating them, again, across different scales and ODDs. So typically you have small scale environments that are constructed of synthetic assets, like you would do in your labs. In the mid scale, you have the option of doing both synthetic environments as well as realistic outdoor off-road environments, for example. And in the full scale, you again have a more diverse set of environments, both for on-road as well as off-road driving. And one of the key aspects here is these environments can not only be generated or created synthetically, but they can also be derived from real world data, which makes possible the concept of true digital twinning of the environments as well. So for example, the CUICAR Greensward area that you see here is one of the digital twins that we have created from data that's captured from real world and then replicated to sub-millimeter level accuracy in the AutoDrive ecosystem. With this, now you also have a variety of user interfaces. So for example, on the right-hand side, you have different human-machine interfaces for observing and interacting with the digital twins. These range from simple flat screen monitors for observation all the way up to XR head-mounted displays. And in interaction, you can go from the basic keyboard and mouse all the way up to a 6 degrees of freedom motion rig, which gives you true feel and motion of how the vehicles are driving. But most importantly, coming to the dev kit now, you have the option of developing the autonomous driving software stacks as well as smart city software stack for on-road driving conditions. And AutoDrive supports a range of APIs to extensively develop autonomous driving and smart city algorithms. And today we'll be discussing mostly about how Autoware is enabling scaling deployments from small to mid to full scale vehicles. So here is a glimpse of or a zoomed in version of the different digital twins that AutoDrive supports. And here you can see them in action, where you have the different scales of vehicle dynamics being simulated differently for each vehicle. Now, for example, small scale vehicles generally have very basic powertrain components, a motor connected by some gears directly to the wheels. But as you go towards full scale vehicles, you have very detailed powertrains. The same applies to other aspects of vehicle dynamics like the suspension geometry and things as such. Apart from that, the sensor suite also changes. So on the smaller scale vehicles, you have sensors that are typically hobby grade or general purpose academic grade sensors. But as you move to mid scale robots, you now have a mix of both hobby grade sensors as well as industry grade sensors. But typically, when you translate to full scale vehicles, you now have the complete sensor suite comprised of industrial grade components. And these now have been replicated to the digital twins so that the development of algorithms can be targeted accordingly. Coming to environment digital twins, again, here is a zoomed in version of the different environments that I just discussed. So we have different synthetically constructed environments for small scale vehicles, typically like boxes or vinyl stickers, or in the case of F110 or RoboRacer racetracks, the air ducts. Uh, One of the environments that is the tiny town is something that we have kept for benchmarking across different scales. And it is basically the scaled up or down version of the same environment across the different scales that you see. Apart from that, yes, you have different mid-scale as well as full-scale environments. Full-scale environments are typically more diverse in terms of their features so that users can target different styles of autonomous driving or different applications of autonomous driving in general. But static environments are themselves not enough. So we have, of course, the option of introducing variability in terms of dynamically changing the times of the day, the weather conditions, or other aspects of the scenario. What you see on the right video is basically a test matrix that procedurally generates and simulates different times of the day. So the top two rows here are going from dawn to dusk to midnight. And the bottom two rows are showing the different procedurally generated weather effects from clear skies to overcast, foggy weather, rain, as well as snowfall. But simulating alone is not sufficient. So you, of course, have the most critical aspect of connecting the digital twin ecosystem with a development framework. And that's what the APIs and HMIs are for. APIs are typically targeted towards autonomous driving applications where, as you see, we have a different suite of APIs that we support. And these will be primarily used for developing the autonomous driving algorithms and interfacing them in real time with the simulator. HMIs are primarily targeted for human in the loop testing and development. And this can be now mixed and matched as well so as to create a mix of autonomous driving and manually driving aided scenarios where you have mixed traffic participants and enabling research or development in those operational design domains. Apart from that, we have also released a few data sets using AutoDrive ecosystem. These are both from the real world as well as the digital twin of the same vehicles. And the one thing that I would like to highlight here is that all of these have been time synchronized from data generation perspective so that not only perception data, but the dynamics data of the vehicles is also usable and could lead to, say, for example, derive surrogate models for different motion planning applications or even control synthesis. One of the key aspects of digital twins is being able to accelerate them, and that's what is supported through the HPC ready simulation infrastructure, where we have different ways of parallelization. Some of them are, as you see, agent parallelization and environment parallelization, where, for example, you could parallelize different environments or agents and isolate them from each other and then scale those deployments. But apart from that, you also have instance parallelization, where you could spawn multiple instances of the simulation itself, which typically isolates the different variables and as vehicle dynamics aspects. And these could be, for example, done in different ways. So here, for example, we have one of the works where we used Docker containers and Kubernetes orchestration using the Rancher cluster to orchestrate parallelized simulation workloads within cloud infrastructure. And here is another representative use case where instead of using Rancher, we now adopted our university's Palmetto cluster using Apptainer as the means of containerization. And here we could now scale the deployments significantly from just 16 parallel instances all up to 32 or even 128 parallel instances. Coming back to digital twins, here we are showing how one could use AutoDrive ecosystem to immerse physical full-scale vehicles in the loop with their digital twins, and support different scales of immersion of the physical vehicle within the digital space. So here you have, for example, pure simulation, which basically, as you already saw, simulates the digital twin and interfaces it with autonomous driving software stacks, where the simulator, typically represented by this block, simulates vehicle dynamics, sensors, as well as the virtual environments. And the real-time data is interfaced with the autonomous driving software stack. You have an emulation mode where the ground truth sensor streams are bypassed using ground truth information. And you can also emulate other kinds of vehicle dynamical parameters and feed them back to the digital space. And the final full immersion phase that's shown in the right graphic is basically the stimulation phase, where the physical vehicle drives on a chassis dyno. Its physical sensors are stimulated using physical stimuli, such as a camera feed rendered using a projector screen, or radar target stimulator from Rohde and Schwartz or other equipment for GNSS stimulation, for example. You can control the independent roller velocities and road loads to emulate different dynamical regimes of operation for the physical vehicle. And then these are now fed back as digital thread back into the digital space. And this loop continues to make sure that the physical and the digital assets are in sync throughout the experiment. So here is a quick glimpse of how it looks. Again, to reiterate, for example, we have the projectors mounted on the windshield of the vehicle that's projecting live feed from the digital space in the front of the vehicle. The physical cameras on board the vehicle are capturing the projected feed and making the vehicle think, or making the autonomous driving algorithm think as if it's immersed in the digital space. The physical vehicle is then controlled using the autonomous driving software stack that's running on board the physical vehicle. Here, for example, we are using Autoware as the validation stack for our experiments, and running a test case of autonomous emergency braking. And as you see, the physical control commands are being relayed in the real world, and the chassis dyno is now making the measurements to feed and close the loop with the digital twin of the vehicle to update the vehicle dynamics within the simulation space. And that now closes the loop to update the projection feed in front of the vehicle. But this is just single agent vehicle in the loop digital twinning. You can now also start exploring interesting use cases from multi-agent digital twinning perspective, and not just pure digital twinning, but mixed reality digital twinning, where, for example, what you see here is only one physical vehicle running in the environment compared to three peer agents and a virtual scenario set up within the digital space that now synchronously performs a multi-agent intersection traversal task. And you can, of course, scale these across different ODDs and operational scales. So for example, the matrix that you see here, the first row represents the test bed, which is the real world. You can have one or more vehicles in the real world, depending on the use case. The state estimation from these is now what's being done using the dev kit, where, for example, you have onboard state estimation algorithms for from small scale vehicles, such as LiDAR based range flow odometry, inertial encoder odometry, as well as full factorial 3D point cloud based localization that's now estimating different states of the vehicle. And then these states are being updated within the digital space to synchronize their digital twins within the virtual environments. And you, for example, have three different use cases. First, for intersection traversal, where you have three other agents co-participating within the same virtual environment. You have an autonomous racing use case where a digital entity of a roboracer vehicle that's completely virtual is immersed in the loop with the physical vehicle that you see above. And finally, for OpenCAV, you have a jump scare scenario where a virtual vehicle is cutting in front of it without any warning, and the digital twin has to sense it and then relay the same action commands within the physical space to make sure that the emergency braking is not only happening from perception side, but actually even within the real world, you have the full factorial test plan that now makes sure that the braking distance is safe and optimum.
So what this enables is two things. One is you don't need the resources in the real world. You can make do with minimal resources. For example, just one vehicle in all of these three different cases. And the second thing is it enhances safety. So for example, you don't really have any of the other peer vehicles in the real world. They are just simulation entities. And as a result, even if your test case is to fail, there is no collision or any other damage in the real world experiment conducted. So now let us see how we leveraged an ecosystem such as this for prototyping the RoboRacer simulation leagues. So we have had three successful deployment of these competitions till now. The first one at IROS 2024, followed by another one at CDC, and then the most recent one being at ICRA 2025 this year.
We got an overwhelming response with over 50 teams registering for each iteration and over 150 participants. And it was really a good experience, not only for us from organization perspective, but the teams who were using the digital twins for developing their algorithms were now able to also perform zero shot sim to real transition in the physical competition. So the sim racing leagues were typically held a week ahead of the actual conference so that the teams could participate in the sim racing leagues ahead of the time and then go to the conference and then participate in the physical racing league. And we also saw some really interesting algorithms as well as the sim to real transition of those aided by the digital twins to win the physical competitions as well.
So here is a typical representation of the participation response that we got. So for example, we specifically for ICRA 2025, which was the most recent competition held, we saw participation from over 150 people across 58 different teams representing 32 different organizations and at a global scale spanning over 25 countries. So it, in a way, validated the practicality and scalability of the competition deployments. But what is more important here is firstly to understand the competition structure. So the structure here is what we believe helped us scale this to such a level. We divided the competition in two different phases. One was the qualification round, wherein we released Dockerized environments for the simulator as well as dev kit to all the teams. of approximately a month ahead of time. And there was a set deadline for all the teams to submit their solutions for autonomous racing, which were then going to be evaluated for their ability to continuously run multiple laps around the track. And the only objective here was to be safe as possible. So safety was most critical, performance was secondary. But then in the competition round, just a few days ahead of the final deadline, we switched the track with another one, and we expected all the teams to slightly modify their algorithms or tune them for the new racetrack, and their algorithm should have already been robust enough for it to be able to handle track changes and other changes in the environment. So here is how the competition framework looks. What we essentially have adopted here for as a best practice is the option of containerization, in which we offer every team the containerized instance of the simulator as well as dev kit. And their job is to just work on this small aspect of developing their own package or packages that can now interface with the AutoDrive API to communicate back and forth. And the primary modality that we used for deploying these competitions is ROS2, which is directly scalable to the Autoware stack. And so some of the teams have also started to use Autoware stack to develop their autonomous racing algorithms and have performed really well in the competition. The other aspect in terms of global scaling is to understand that not everyone would have computational resources that are state of the art. So we offered the teams the option of distributed computing as well as GOI versus headless modes of computing to better efficiently develop their algorithms, and whatever solutions they could submit were still valid when we deployed them and executed their solutions. The final aspect of this competition was to be able to transparently record all the key performance indicators for the vehicles as well as the race in general and provide this data back to the teams. And in addition to that, what we now also have the capability of is to analyze this data, which is pretty detailed in terms of all of these different KPIs that we have, as well as be able to now comment on the reproducibility and benchmarking aspects of the simulation and the testing of different autonomous racing or driving algorithms in general. So with that introduction and overview of AutoDrive ecosystem and its applications, let us now move to the specific topic of interest, which is its integration with the Autoware stack. So the main reason or the main motivation that we had for doing this was our first encounter with the Autoware stack when we came or started our PhD at CUI car. We encountered this vehicle that is a part of our lab, which is the Open Connected and Autonomous Vehicle or OpenCAV. And it is basically a Chrysler Pacifica retrofitted with sensors, drive-by-wire, and onboard compute, which can enable autonomous navigation throughout the campus. So we already have a pre-computed map of the campus environment now, and we can use that map for localization. Once we have the localization estimates, we can then drive this vehicle around from point A to point B in the campus and record that trajectory, or we can also do an online or offline trajectory planning to navigate from one point in campus to the other. And with that plan now, what we can do is offer autonomous shuttle rides for people from one point in the campus to another. So what you see currently in action in the video is the capability of the vehicle running the Autoware stack to map the environment, then generate the trajectory, and then track that trajectory in real time, all autonomously to navigate from one point on the campus to the other.
And this is what basically paved the way of starting the development and integration of the Autoware stack with AutoDrive ecosystem, where, as you already saw, we first had to model the digital twin of the OpenCAV vehicle and then interface it with the Autoware stack, much the same way as the physical vehicle runs the Autoware stack, so that whatever you develop in simulation can be tested rigorously before deploying it onto the physical vehicle. But most critically, the deployment from simulation to reality should not have any changes, either in terms of the algorithm or even in terms of the interfaces. For example, the topics that the Autoware stack is publishing on, or the sensor streams are coming on, or other hardware software integration aspects. And that's what was the key motivation, which firstly required high fidelity digital twin of the OpenCAV, and secondly required the API for AutoDrive and Autoware to be integrated harmoniously so that the deployments from simulation to reality became seamless and zero shot.
Finally, once we had this working for the OpenCAV vehicle, we wanted to now have a uniform or a unified pipeline or a framework that can support deployment of a common autonomy stack such as Autoware across all the different scales and operational design domains of autonomous vehicles that we typically encounter with during our research. And so as a result, what we did was, with all the different digital twins that we have, we created a corresponding Autoware API for them so that they can be interfaced with the Autoware stack across small, mid, and full scale, while targeting different operational design domains like on-road navigation, autonomous racing, as well as off-road navigation. So let us now delve into each of these aspects. All the different demos that we will be showcasing hereinafter are going to be following the same three-stage autonomy deployment pipeline, starting with mapping of the environment, then generation of the trajectory, and then finally tracking that trajectory in real time. And we will show demonstrations of how we were able to achieve the deployments with AutoDrive Simulator, followed by deployment in AutoDrive Testbed, which is the real world. And just a small highlight for all of these different videos is that these are not just demos. These are in fact fully recorded tutorials that we have released, and we will talk about that in a greater detail. So with respect to the F110 vehicle or the RoboRacer vehicle, here we completed the first stage of environment mapping. Next stage is recording the trajectory. So we have the map-based localization estimates engaged, and what we are able to do now is just drive around the racetrack to collect the waypoints, and that will serve as our reference trajectory. Now this can be done either manually, such as the demo currently showing, or it could also be employed for map-based raceline optimization, which can be a better approach for autonomous racing deployments. And we saw some of these approaches in the Sim Racing League, which was very interesting and satisfying to look at. So once we have the entire trajectory plan or an optimal race line, what we can do is use the Autoware stack to now command the vehicle to track that trajectory autonomously, again, while localizing with respect to the map in real time. And one aspect with respect to this operational design domain is that we are not just navigating from one point to the other. We need a continuous way of completing multiple laps around the racetrack. So what we need to do is keep a track of our pose estimate and not just stop at the endpoint of the trajectory, but also try to complete an entire loop multiple times, which is required, for example, in a time attack race where you have multiple flying laps to register the fastest speed. With that deployment in the simulation, we also evaluated it in the real world.
Now, again, to highlight, this is a zero-shot sim-to-real transfer, meaning we have not changed or tuned any perception parameters, like, for example, the LiDAR covariance matrices or any other aspects of the localization algorithm. And we have not even tuned any of the control parameters like the vehicle control commands or controller gains. And all of the things that you see are being transferred zero shot with the same parameters that they were simulated in. One more thing that you can, of course, observe here is that we have a completely different track between simulation and real world, but the pipeline still as should work. It is working in the real world without any modifications to the parameters. So again, the second step was that of recording the trajectory. And finally, here we have the pre-recorded trajectory being loaded, the vehicle being localized within the map, and then driving autonomously using the Autoware stack. And one more small thing here is everything's running on board the physical vehicle. So in the simulator, of course, yeah, you can use a high-end PC to deploy your stack and the simulator on. But the idea is that all of these software stacks should be edge deployable, and that's what you see on the physical vehicle, where we are using the onboard computer for the RoboRacer to deploy the Autoware stack.
Now coming to the second vehicle, which is Nigel. Here we devised a slightly different example because the operational design domain that this vehicle targets is that of on-road autonomous navigation. So first of all, what we are doing is just exploring the environment and creating a map out of it, which will then be used for the trajectory generation, localization, and motion control task. Once we have the map, we can move forward with trajectory recording. And here what we are essentially doing is recording the localization estimates of the vehicle and driving it from the spawn location to one of the designated parking lots. So this application is essentially demonstrating an autonomous parking application. And once we have that plan, either via a pre-recorded example or by a motion planning strategy, we can then engage the vehicle in autonomous mode to navigate from the spawn location all the way up to the designated parking lot. And similarly, as with the RoboRacer vehicle, we were exactly able to deploy this in the real world, zero shot, without modifying any perception or control parameters.
So here, for example, you see the real world mapping in action, followed by recording the trajectory from the spawn point to the designated parking lot. And then finally asking the vehicle to do the same autonomously in real time using the Autoware stack that's deployed on the physical vehicle. So these were some of the small scale deployments. Next, we move to mid-scale vehicles. For example, the Hunter SE by Agilex. Here again, we are mapping the environment, but this time we are using a different approach. So as you see in the simulation, we have a 3D LiDAR that's mounted on the robot, but we are using only a 2D slice of the 3D point cloud to actually create a 2D occupancy grid map. And the reason that we are doing this was to analyze the effect of environment representation in terms of mapping. Since you have a simplistic environment which can be typically captured in a 2D plane representation, such as the 2D occupancy grid map, we wanted to see if that was enough for the vehicle to be navigated from point A to point B and park autonomously, similar to Nigel, what you saw earlier. Or was it truly necessary to have a 3D map? And turns out you typically don't need a 3D map unless the environment is very complex and you have different objects that are either lower or higher than the 2D slice that you are capturing. So here with the 2D map, we are now localizing the vehicle and driving it from the spawn to the targeted parking lot while recording the trajectory so that the autonomous driving algorithm can now move the vehicle much the same way from the spawn point to the designated parking area, but autonomously using the Autoware stack. And once now we have this working in simulation, we could transfer this similarly to the real world. But what's more interesting is to deploy this in much complex ODD, such as off-road driving. And that's what we typically explored in this use case, where you have a very detailed off-road environment full of ridges, trees, even a pond in the center of the map. We use AutoDrive Simulator to directly create a point cloud map from the ground truth sensor simulation within the simulator. Of course, you can use Autoware stack to do the same, but here we are just demonstrating one of the advantages of digital twins. And then what you can do is directly start from trajectory recording phase rather than investing your time in mapping. As long as you know that the digital twin that you have is in fact a true representation of the physical deployment that you have in mind, this should work out of the box. And here you can see the trajectory recording in action, where we are teleoperating the vehicle from the spawn location to a designated point in the environment, which if traversed linearly would go through the pond. And finally, we are then asking the Autoware stack to try to navigate the off-road environment autonomously. And so this is basically expanding the operational design domain of Autoware stack, which has been pretty much explored in on-road driving conditions, to the off-road now to enable off-road navigation in an end-to-end setting in a simple cutesy example or demo that you are seeing. And of course, this can be now complexified in terms of both the environment or the vehicle, but more importantly, also leveraging other aspects of the Autoware stack, the different object detection, localization, or control methods that Autoware offers to come up with more and more efficient means of traversing the off-road operational design domain. Finally, going full scale, we have the OpenCAV that we started with being simulated in the same benchmark tiny town environment. Here again, we are analyzing the effect of 3D versus 2D perception. So here we are using the 3D LiDAR, but creating a 2D occupancy grid map of the environment from the thin slice of the point cloud. As you can see, as we scale the deployments and inject sensor noises that are realistically sampled from real world data, we can start seeing different variations in terms of mapping. So for example, the smaller scale vehicles would have different resolutions of the map compared to the full scale vehicles. And storing those maps now becomes difficult. If you keep using the same resolution, the scale of a full scale environment will typically limit the storage size of the map or even onboard computation if that's happening in real time to create the map in the first place. And that is something that you have to be mindful of while devising your algorithms. And so changing the resolution, changing the scale of the map becomes important. Next, you have the same way of generating the trajectory from point A to point B. Again, because OpenCAV is representing an on-road commercial vehicle, we are targeting the autonomous parking operational design domain, where the vehicle is taken from its spawn location to a designated parking spot. and then asking Autoware stack to do this autonomously uh, using the 2D map in this case.
One of the key challenges that we observed while implementing this was that the tolerance between the lane bounds that we have for a full scale vehicle was pretty tight. And so as a result, it was very difficult to come up with the tuning parameters for the autonomous navigation case study. Both in the case of 2D navigation example that we just showed, as well as the more realistic demonstration of the same application in a downtown like scenario, wherein we start off with constructing a 3D representation of the point cloud data and use that for recording the trajectory based on the localization estimates of the vehicle. And it is now starting to become a bit noisy because of the complicated representation of the environment.
And even the roads here are not completely flat, so it kind of brings in the powertrain dynamics of the vehicle in play, where you have transmission upshifts and downshifts depending on the gradient of the road, and that plays a crucial importance in terms of ensuring whether your algorithms can be scaled to the real world or not, because the physical vehicle would have those effects in the reality. And finally, here as well, you are seeing the Autoware stack completely controlling the digital twin of OpenCAV fully autonomously to take it from the spawn location and drive it all the way across the road, across the intersection, and then into the parking space, and then parking it autonomously within the designated parking lot.
And finally, as we demonstrated earlier, the algorithms that have been developed or fine-tuned in simulation or with respect to the digital twins alone can be deployed into the real world directly, or using a mixed reality digital twin interface, or even with vehicle in the loop setups such as the AVL driving cube. So all the different examples that we showed earlier have all been open sourced, and we have a dedicated GitHub repository as well as a complete YouTube playlist that guides step by step all of these different examples as well as the general interface of AutoDrive with respect to Autoware. So for example, the first video in here is demonstrating the high level interface of the repository with documentations for each and every vehicle and instructions for deploying this either with the digital twin or in the real world. And the second video is an example of one single vehicle, in this case OpenCAV, to demonstrate the documentation of the entire example and workflow that one can follow to recreate or replicate the results. But map-based autonomous navigation examples that we just showed across the different scales or ODDs is just the beginning, and this integration can enable more complicated approaches to be deployed with AutoDrive and Autoware. And we hope that this stepping stone serves as a starting point for us to now explore some of these challenging problems in the space of autonomous driving or racing. Finally, as another resource, what we have created is a full length video of about 15 to 20 minutes that spans across the entire setup and installation of the stack, including AutoDrive as well as the AutoWare stack, across either local installation or a containerized installation, or even installation on devices that are typically employed on board the autonomous vehicles. And highlights each and every step of the way, starting from example, the Google search regarding the resource, all the way up to implementation and testing that the software stack is in fact installed correctly and working as expected. And finally, even all the different demos and examples that we just showcased very quickly in today's presentation, but it could all be explored at one's own pace, and the results could be easily replicated.
Now for the exciting part. Today we are unveiling a new digital twin that will be released in AutoDrive soon. And that is the digital twin of one of the very famous platforms that Autoware supports, which is the PixKit. So here you have a complete digital representation of the PixKit, which is calibrated from the real PixKit that we have in our lab, both in terms of its high fidelity vehicle dynamics and sensor physics that you see in action, as well as the different interfaces and data that comes in and out of the vehicle. Here, for example, you have the same steering mechanisms that the physical PixKit has. The front wheel steering like a normal car, four-wheel steering which can turn in tighter spaces with out-of-phase steering for the front and rear wheels, as well as the wedge wheel steering which enables the PixKit to crab walk across the road and change lanes without changing its orientation. So one could now start developing the planning and control strategies for such different skateboard chassis architectures. You also have different lights and indicators being simulated, which is something that Autoware stack is fully compatible with, and now can not only be useful for developing or designing autonomous driving algorithms, but also signaling smartly other traffic participants, including humans or other autonomous vehicles, to relay the intentions of the ego vehicle. And finally, here is just a glimpse of the digital twin in action, where we are just driving it across the tiny town benchmark environment. But again, this is just the beginning, and you could put the same PixKit in any other environment. You could even recreate, as I said, using real world data. We have pipelines to recreate physical environments pretty quickly, which can enable you to virtually prototype your algorithms for the task that you are having at hand. With that, we conclude our presentation and would be happy to answer any questions at this point. Thank you.
Okay. Thank you very much, Chinmay and Tanmay. That's very great presentation. We don't have much time because of the delay at the start, but does anyone have a question? Yeah, okay. Then let's open up. Is there any questions from the audience? I just have a question then, Chinmay, about the Autoware integration. You're doing on-road and off-road and parking. Are you using free space planning in Autoware, or are you using any of the Autoware planning algorithms?
So right now we are in the process of exploring the different planning and control algorithms in Autoware. The demonstrations that we showcased as a part of these different examples, they included some of the SLAM methods, as well as pure pursuit and Stanley control applications in the context of the different demos. But going forward, what we are planning to do is try to integrate or implement and test the different perception planning as well as control applications, especially for the mid and full scale vehicles, which typically have the types of sensors that are supported by Autoware stack right out of the box, and then study the deployment of those algorithms into the real world so that we can benchmark the simulation as well as real world performance and comment on the sim to real transferability of these approaches.
Okay, great, thank you. And just to follow up then, it seemed you're sometimes using 2D localization and sometimes using 3D localization. Are they both available through your AutoDrive branch in Autoware?
Yes, they are both available, and we have documentation for both the different examples concerning 2D or 3D perception with respect to the LiDAR point cloud.
Great. Well, thank you very much then. If there are other questions on the audience, yes.
Want me to come there?
Yeah, I just, can you hear Tanmay this question?
Yeah, you know what I'm saying?
Not really. Could you
So
try
yes,
repeating it?
Come forward, yeah. Okay.
Thank you for that presentation. It was really informative. Just like a quick question, in a couple of the early slides, you talked about how you can do like different weather conditions. Just wondering, is the weather conditions only change like for the perception, or does it also change the dynamic? So it's like the friction between the tire and the roads. Is that affected as well?
Yes. So yes, it can be affected. Both perception and dynamics of the vehicles can be affected for the different weather conditions that you saw. And as a matter of fact, AutoDrive is completely open source, in case we didn't mention it earlier. So anyone that's interested in developing more detailed models of weathers or the environments or even environment vehicle interaction, different terra mechanics simulations can now go in the source of the simulator and develop their own behaviors and models as well. So yes, to answer your question, yes, it affects both the perception and the dynamics. But in case you are more interested towards detailed simulations of those aspects, you can of course develop and simulate your own models in there as well.
All right,
What we
perfect.
have tried to do is based on the friction maps from the real world data for different wet and dry conditions for on-road and off-road driving. We tried to replicate those into the simulation so that we have a different vehicle behavior when the road surface is dry, for example, and when there is rain or precipitation, the braking distance or other traction properties for the vehicles are in fact affected.
Thank you.
Okay, thank you very much. And yeah, let's all thank Chinmay and Tanmay for that great talk on AutoDrive and Autoware.